All right, so the recording is now started. Welcome to everyone who is joining us online. Okie dokies. So we're just going to go ahead and start with some questions from section 2.4. All right, so section 2.4 is talking about the second derivative. So we're going to start on, let's see if I can get my pen to work. We're going to be on page 115. And we're going to do some practice problems. We are going to start with problem 2. So in this problem, we have a graph of a curve. And we're asked to figure out at which of these points both dy dx and d squared y dx squared are negative. So I'm going to label these points real quick. This is kind of what the graph looks like. All right, so we are looking for the place where both the first derivative and the second derivative are negative. How would we start approaching this problem? Like, what would you guys suggest doing? If you have any ideas, just go ahead and put it in the chat box. Okay. Well, my first reaction is to find out, I have these two conditions that need to be met. My first reaction is to figure out which one would be easiest to eliminate some points from. And I think that's going to be figuring out where the first derivative is negative. That way we can kick out some of these points and narrow it down. So which of these points have a negative first derivative? Okay, well, we can start off by picking which ones are 0. So D has a derivative approximately equal to 0, or equal to 0. And then in the chat box, we just have A is negative, and E is negative, and that's right. So points A and E have negative first derivatives. So that means that we know D, C, and B cannot be the answers to this question. That leads us to ask which of these, A versus E, is going to give us a second derivative that is negative. So now we're looking at the rate of change of the rate of change. So we're looking for, there is going to be a first derivative, and that first derivative will be becoming more negative, right? So what are you guys thinking? Which is going to have a second derivative that is negative? E, you're right. E is the point that we're looking for. Because if we kind of draw this tangent line for A, and then we draw this tangent line for E, what we need to look at is what's immediately happening right after that. So as x increases, is this tangent line going to flatten out and get closer to 0 and then become positive as it does in this area right here? We can see that these tangent lines along this curve are getting close to 0, and they are 0 right here at the bottom of that curve. And then for E, we know that the slope continues to go down, so these tangent lines are going to continue to become more negative. So we can see that the rate of change of the rate of change is going to be negative. All right, good one. Let's take a look at problem. Let's do 4 and 5. So in these problems, they give you a graph and they ask you to determine the signs of the first and second derivative, positive, 0, or negative. And for these functions, they'll be positive everywhere, 0 everywhere, or negative everywhere. All right, so what do you guys think for number 4 and number 5? Let's start with number 4. Is the first derivative? Yep, the first derivative is going to be positive. And the second derivative? Also positive, exactly. What about 5? Yep. This first derivative is 0 because it's a flat line. It's already a constant if we look at this equation. We were kind of discussing last week how we can bounce between like parabola, line, constant. In this case, it's just a flat constant, so dy dx is going to be 0. And what does that say about the second derivative? Also 0. Exactly. So basically, this is kind of doing basically what we were doing last week. We're just doing it again. And sometimes it's a little harder to visualize, but yeah, basically that's the concept. All right. Now let's do 17. So this is going to be on page 116. We have a table that gives us the number of passenger cars. C is equal to f of t. So number of cars is equal to the function f of t. In millions in the US in the year t. So part A is asking us, do f prime of t and f double prime of t appear to be positive or negative during the period of 1975 through 1990? Do you guys all have your books with you so you can see this table? Awesome, okay. Just notation-wise, this is here, our first derivative, and this is our second derivative. Excuse me. And so what are you guys thinking? We're looking at the years between 1975 and 1990. So T is increasing by 15 years, and C goes from 106 to 133, and that's in millions. So what does that kind of say about the rate of change between 1975 and 1990? Okay. Well, or let's call this F. That's what they wanted to call it. So F of 1975 is going to equal 106. And then we have F of 1990 is equal to 133.7. Okay. basically, we don't really have the tools, especially based on the fact that this is a table and they haven't given us an equation. We don't really have the tools to do this in any other way than estimating. We're on page 116. In section 2.4. Basically, what we can do is look at average rate of change and use that to kind of extrapolate what we think the instantaneous rate of change is going to be. So in this case, I'm going to look at delta y over delta x, or in this case, it's going to be delta c over delta t, because we have cost changing in the y-axis and time changing in the x-axis. That being said, we can roughly calculate it like this. And then 1990 minus 1975. The end result of this is going to be what? 30, I don't have a calculator on me. So that's 27, right? Something like 27 over 50. And what we know about this is that it's positive, right? Because this number is smaller than this number. So we know that our first derivative is going to be positive. And we can tell that just by looking at what the average rate of change kind of is. Okay, that being said, what are we going to look at to determine if the second derivative is going to be positive or negative? What are we going to have to analyze to figure that out? We're going to have to look at how it changes on a smaller time scale. So we're going to have to compare I'm going to take away that delta because we're going to have to compare I can remember the equation for average rate of change. It would probably be helpful. Get it in the right order. I'm going to have to compare this one to this one. And so on and so forth. And the way that we're doing that is we're kind of breaking it up so that we can see how the average rate of change changes during this period of time. Is everybody following what I'm doing and why? Awesome. Okay, so this is going to be 121.6 minus 106.7 over 5. This is going to be 127.9 minus 121.6 over 5. And this is going to be 133.7 minus 129 over 5. Okay. So here we can tell that it's going to be pretty large. This is what, 6, that's about 15, approximately 15 over 5. I'm not really going to think too hard about what exactly these numbers are. This is approximately 6 over 5, and this is what, I'm just ignoring these decimal places. I don't really have the energy for that right now. So this is approximately 6 over 5. So what is that telling us about the second derivative? How does the change from here to here differ from the change from here to here? it's growing a lot faster right here, right? It's growing very fast, and then its growth rate kind of slows down, and then the growth rate kind of stays about the same. So if we were to kind of sketch that out, what we could see is here, starting at 1975, it's growing very quickly. And let's call that like 1980. We're going from 106 to just over 120. And so, or 100, let's just call it 121. So it grew very quickly. And then it kind of tapers off. We slow down. We kind of have a constant rate going here between 85 and 90, and we only move up to about 133, right? So obviously, is this the most precise way of determining how exactly this is, what exactly this is? Is this exactly what the graph looks like? No, but we are able to tell that it is slowing down. The growth rate is slowing down. So what we can say from that is that f double prime is negative. All right. So now it's asking us to do essentially the same thing between 1990 and the year 2000. So I'm going to erase some of this, and we're going to kind of go through that process again. And we're not going to go ahead and do all of the algebra for this. We're going to see if we can kind of use like the same logic, just without the numbers. Sorry. All right. So for the years 1990 to 2000, we have a little bit of a smaller time scale here too. 1990 to 1995, we're looking at it's going down first of all. So from 1990 to 1995, we're looking at a negative rate of change. And then from 1995 to 2000, we're looking at a positive rate of change. If we look at the average rate of change between 1990 and 2000, what do you think that is? We can go ahead and just like write it out. We have 133.6 minus 133.7 over 2000 minus 1990. So that's going to turn out to be 0.1 divided by 10. So this is it's a tiny number, but we're going to just call it approximately 0 because we don't really need that tiny number in our lives. So that too is kind of how we're going to describe the derivative for the period of 1990 to 2000, because the derivative in that period, depending on the year, is both positive and negative. So we know that between 1990 to 1995, it's negative. And between 1995 through 2000, it's positive. So we're just going to call it a wash, and we're going to call it 0 because that's basically what the average rate of change is, okay? So yeah, I'm not really the hugest fan of the way that this question is phrased, because it's asking you to find an instantaneous rate of change at a like at a time period where it's changing in between. So if we were kind of going to sketch out that graph, yeah, this is a really poorly phrased question. Not a huge fan of this. But if we're going to kind of look at this graph, we're going to call this 1990. We're starting all the way up here at 133. Here's 128. There are 1990s up here, 1995 down here, and then 2000 is up here. So that's kind of what our graph looks like. And we know how to like work with graphs that look like this because we've done graphs that look like this before. But to ask us to figure out what the derivative is generally in this period is just kind of not a great question. Anyway, so what about the second derivative? Yes, the second derivative, it's like going down steeply here. It becomes less steep, less steep, less steep, approaching zero, and then gets like strong, like more positive, more positive, more positive. And we know that just because of the way that we kind of sketched this out. So you're right, the second derivative we're going to call positive. All right, so part C, it's asking us to estimate f prime of 2005. Using units, interpret your answer in terms of passenger cars. The best way to do this based on the numbers we have is just to find the average rate of change between 2000 and 2005 because those are the numbers that we're given. So a lot of the times when they say estimate the derivative or estimate the instantaneous rate of change, they just mean find the average rate of change, because that's really all you can do. So this is 136.6 minus 133.6 all over 2005 minus 2000. This is going to be 3 over 5. And this is .6. So if we're going to interpret this answer in terms of like what this equation is actually talking about, it's asking us to, like, this equation is giving us like how many cars are in the US in year T. So in the year 2005, there are 136 million passenger cars. And we can estimate that that number is going to be going up after 2005. And we're guesstimating that for every year that passes, there are 0.6 million, or what is that, 600,000 more passenger cars per year. So what we're estimating is that in 2006, there will be, that's 136.6, so there will be 137.2. And so that's kind of what we're saying, is that as every year, like as years increases, we know what will happen to the amount of passenger cars, and we can estimate exactly how many cars that would be. Is this the best estimation? No. It's not a great estimation because it's done for a fairly wide period of time, but it's the best that we can do. So that's what we've got. Okay. Are there any questions about how this whole shindig went down? Awesome. Let's move on to section 2.5. So this is talking about marginal cost and revenue. And this is kind of going to I guess it's depending on your opinion of marginal cost and revenue, is kind of going to haunt you, or it's kind of going to make your life better throughout the course of this class, because marginal cost and revenue will stick around. And it's basically a different like calculus way of like writing down things that you already know. So when they say marginal cost, what they're talking about is the derivative of cost, right? And when they say marginal revenue, they're talking about the derivative of revenue. So I am currently on page 122. And we are going to talk about question 2. The function C of Q gives the cost in dollars to produce Q barrels of olive oil. A, what are the units of marginal cost? And B, what is the practical meaning for the statement MC equals 3 for Q equals 100? All right, so what are the units of the marginal cost? Any ideas? Okay, so barrels is going to be the units for Q, so the quantity of barrels of olive oil. So barrels is going to be that unit. What we're looking at with marginal cost is we're looking at a change. Let's explicitly write this out. Okay, so what we're looking at here is that C prime of Q, so the change in Q, or if we're going to write this in Leibniz notation, we were kind of doing this last week, this would be dC dQ, right? So this is the derivative of cost with respect to quantity. And then that's going to be our marginal cost. So let's kind of walk backwards through this. We start off here, we're looking for units of marginal cost. That means we're looking for the units of the derivative of C, and that will kind of bring us to the derivative of cost with respect to quantity. And that will be the cost in dollars per barrel of oil. So what this kind of means is that, let's imagine we have a certain number of, like Q number of barrels of olive oil that we're producing, and we're going to increase that to Q plus 1. How is C going to change? Well, C is going to change based on the derivative, and it's going to be in dollars per barrel. That makes sense? Awesome. So for every barrel of olive oil, what is the cost of adding one more? It's that sort of like concept. Cost per barrel. So B, what is the practical meaning of the statement MC equals 3 for Q equals 100? What do you guys think about that? So I'm just going to go ahead and write this in a statement form that I'm a little more familiar with. I don't usually use marginal cost like as MC. I usually think of it almost exclusively in terms of C prime of Q. Okay, so what we're not looking at is $3 for every 100 barrels. What we're looking at is what's going to happen if we add one more barrel? What is the cost for that one extra barrel? Yes. So We don't actually know. We don't know what this is. We don't know what the cost of 100 barrels is. But here, I'm going to write 100 in there. So we don't know what a cost of 100 barrels is. But we do know that the cost of 101 barrels is going to equal the cost of 100 barrels plus 3. And what's happening here, I'm going to kind of sketch out a little graph. So say this is some number. I don't know what number this is. I'm just going to call it cost. So whatever number this is going to be C plus 3. And we know what's happening here is, and it doesn't matter what this graph is doing before or after, because all we're concerned about here is the cost of adding one more barrel to our production, and the cost of that one barrel is $3 for the barrel. Okay. I hope I explained that well enough. Does it conceptually make sense as like what we've been discussing in terms of derivative? The rate of change between 101 and 100 is going to be 3, but we're just explicitly stating that it's cost and quantity. Okay. Okie dokies. So let's take a look at question 8. So this will be on page 123. So we have a figure 2.57, and it shows a graph of cost and revenue for a car manufacturer, and it's asking us to determine which is greater, marginal cost or marginal revenue at Q1 and Q2. So I'll kind of sketch this out. Feel free to put any thoughts you have in the chat box. Okay. Thoughts? All right, so at Q1, MC is greater. Can you kind of explain that for me? We're looking at this point. Why do you think that marginal cost is greater at Q1? Okay, so you weren't looking at the slope, you're looking at the value. Yeah, so I think what we need to just do here is look at like what the slope is. because what the slope is going to be the whole kind of question. The slope for C is going to be smaller than the slope for R, correct? And we know that the marginal cost is going to be is equal to C prime cubed. Let's see if I can actually write this equation correctly. So when we're looking at this equation, basically what this is saying is that, so we're going to start at this point, and then we're going to go like one greater. And then we're going to find out the difference in like y value between these points, right? And that difference is going to be the marginal cost to add one more. Basically, the point that I'm trying to make with this is, in comparing it to marginal revenue, it's the same sort of principle. Marginal revenue is going to be approximately equal to R cubed plus 1 minus R cubed. Even though this initial R value is going to be smaller, the cost to go from, or not cost, the money that you get from going to R cubed plus 1, this marginal revenue is going to be greater for R because the slope is greater. And basically what this phrase is saying is that it doesn't matter what value you start at, because all you're looking at is the difference between the values. And that value is, like, it matters based on the slope. So the slope of R is going to be greater. The revenue gained going from Q plus 1, the revenue gained from going to R of Q to R of Q plus 1, or in this case, R cubed 1 plus 1, is going to be greater than the cost of making that same jump. So basically what I'm saying is that the slope for R is greater, so R is going to be greater than MC. And what do you think that says about Q2? At Q2, it's going to be the same. Because these are lines, the slope isn't changing, so the slope of R is still going to be greater than the slope of C. So still, if we go to Q2 plus 1, we're getting more revenue, so our marginal revenue is greater than the cost of doing so. Yes, exactly. Ralph has it. Okay. All right. So I mixed this question up with another one. It was supposed to be a very insightful question, and I should have asked question 12. Sorry, it's been a little while since I've gone through this section. So the question I meant to ask and actually have a meaningful discussion about was question 12, because that will kind of give us a much better insight into. I knew it was one of the ones with the graphs. I just kind of went all in question 8. Really wasn't that useful, just linear. Question 12, though, we're going to be asking about two graphs and asking the question whether or not we should add another bus. Because we're looking at a charter bus company. So I'm going to quick sketch out this. That's a really ugly line. So that's going to be our revenue stream, and our cost is going to look something like this. This is C of Q, this is R of Q. All right. So it's asking whether they should add a 50th bus. So that would give us the information that we already have 49 buses, and it's asking whether or not it's a good idea to add a 50th bus. So here's our line for 50. And so we're right now hanging out at 49. Basically what we need to figure out is marginal cost. What is marginal cost and marginal revenue? Because conceptually we know that profit, that's not a P, that's an R, profit is going to be equal to revenue minus cost, right? We can kind of conceptually just work along the same things. Marginal profit is going to be equal to marginal revenue minus marginal cost. So if our marginal revenue goes up, but also our marginal cost goes up, how does that affect our marginal profit? And we want to, as a company, we want to maximize this because we want to be making as much money as we can. So if our profit is going to go down, going from 49 buses to 50 buses, or our marginal profit is negative, that's another way of putting that, then it's not something we want to do. First of all, if we're looking at both 49 and 50, how are we sitting? Our revenue is higher than our cost, right? And that's what we want as a company. So our revenue is at about 400 and our cost is, let's call that like 250. So what is going to be our marginal cost here? One way that you can kind of do this is just draw a little slope for your, draw your little tangent line and kind of look at that slope. You can tell that it's not a very high slope at all. You could actually figure out what the slope is. That would be 200 divided by 25, which is 8. So for revenue, we have a constant is constant, right? And that's given to us because R of Q is a line, and that's constant 8. Now the question is marginal revenue greater than marginal cost? What do you guys think? Should we add that 50th bus? Is our marginal profit positive? Will we get more profit if we add that bus? Yes, we will. So we know that we should add the 50th bus. Now let's look at sorry, that was a really not straight line. Now let's look at the 90th bus. So this is going to be 100. I'm going to kind of estimate where 90 is. I'm going to say that this is approximately 90. So that is saying that we're currently sitting at 89 buses. Should we add the 90th bus? Let's do that same process. We have to ask ourselves, is the marginal revenue greater than the marginal cost? Kind of draw ourselves a little tangent line. What do you guys think? Is our marginal profit positive? Is marginal revenue greater than marginal cost? Okay. This is our revenue right here up top, and the slope of our cost tangent line is going to be greater. So the answer to this is actually no. Yeah. So because we're looking at this point, because the slope is so steep here, the cost is kind of skyrocketing for adding more buses, but our revenue isn't skyrocketing. Our revenue is staying pretty solid. So our marginal cost is going to be, yep, that's a big area where it's easy to get mixed up in this kind of section, is mixing up marginal cost and actual cost, and marginal revenue and actual revenue. That's one of the reasons that a lot of the times I do write things out as R prime of Q and C prime of Q, because it's a little bit more difficult to mix them up that way, especially if you want to write them in Leibniz notation. But principle is kind of the same. We're going to say that because the slope of C of Q right here is so high and R of Q is not increasing at that same rate, that our marginal profit is going to be an R, not a P. Marginal profit is negative, or our marginal revenue is less than our marginal cost, and therefore we should not add the 90th bus. Okay. How is everybody feeling about this kind of stuff? I think these are the only two sections that we had for this week, unless I'm mistaken. So this is really all I have for you. Yeah, a lot of this class is just having the need to practice and practice and practice, because a lot of this stuff is just material that you just need to become, like, you'll get much better at it as you get more, like, intuitively familiar with it, which is, you know, a big time consuming experience, but it's kind of how this class works. So, yes, the big takeaway from chapter 2.5 is to remember that marginal is equal to slope, marginal is equal to derivative, derivative is equal to slope of tangent line. So, so that's kind of your thought process for this type of problem. So yeah, any more questions? If not, I guess I'll just kind of let you go. All right, it looks like it was a short lesson this week, so okie dokies. You guys have an excellent weekend, or I guess the end of the weekend, so you guys have an excellent week. I hope you guys have a good evening.